All right, hello everyone. We're gonna finish up section 15.9 today. Okay, a few more examples. So here come one. Evaluate. This one, double integral over the region d x plus y ex squared minus y squared a where d is the rectangle enclosed by the line x minus y equal to 0, x minus y equal to x plus y equal to 0, x plus y equal 3. From the description of region D, we can figure out u and v. U is equal to x plus y, v x minus y. Okay, region S. U is equal x plus y, v equal x minus y. I'm just gonna add them up here. ADD add. U plus v is the 2x, so that means x is half of u plus v. Okay. Oh, the other one, I'll just do the same thing here. U equal x plus y, v equal x minus y. So instead of adding, I'm gonna be subtracting it. Completely okay to subtract if you don't like adding. Because subtract is just add to the multiple of -1. It's the same thing. U minus v is equal to 2y. So I mean y is half of u minus v, and then from there we can figure out the Jacobian. Ij partial x with respect to u, and then partial y with respect to u. Partial x with respect to v. Partial y with respect to v. Partial x with respect to u is going to be 1/2. Partial x with respect to v is 1/2. Partial y with respect to u is 1/2. Partial y with respect to v is -1/2. Okay. So we have a minus minus, so oh yeah, minus 1/4 minus 1/4. You need the absolute value here, or else you're not going to get a positive answer. So it's going to be negative 1/2, so it's 1/2. Next step is the, well, we can do a conversion now. Double integral over the region D x plus y e x squared minus y squared dA is equal to, well, now here comes the region S there, right? Double integral over the region S, x plus y is u, and then e x squared minus y squared is the, you know, uv. dA is the du dv, and then u go from 0 to 3, v go from 0 to 2. Put it in here, set some time here. 0 to 2, 0 to 3, du dv. Oh, switch them, make your life easier. So you can see the integral here, and then I'm going to pull out the half outside. Okay, uv dv du. Now it look better. Okay, so you can get this thing done with the u-sub 1/2. We already have the u here. I'm going to do the t-sub here. Okay. So this is going to be a u times 1 over derivative with respect to v is going to be so it's going to be 1 over u. Oh, euv. Yeah. Yeah. Okay, so sub in 2 is going to be a e 2u minus e0, which is 1. du. It's better now. And then I'm going to do another u-sub here. But this u, so it's going to be the t-sub. Okay. Half e 2u minus, well, u. Oh, I thought I needed another parameter. I don't need it. 0 to 3. Half of 1/2 e 3 times 2 is 6 minus 3. Okay. Now I definitely need another potency here. 0, so half of e to the power 0 minus 0. Yeah. Let me draw out D. Unlike the previous example, we use the integrand to figure out U and V. Look at the triangle here. There are three vertices, right? Triangle have three vertices, so we can use the transformation to sketch our region S here. So that's I'm gonna do at 0, 0, right? U is equal to 0. V is equal to 0. UV. Okay, so do different colors so you see. At, oh, actually, I'm just gonna do it right here. Next point is the 0, 1. U is the, okay, so x equal to 0, y is equal to 1, huh? 2. V is equal to x equals 0, y is equal to 1, 4. 2 and 4. At 2/3, 0. U is equal to, okay, so x equal to 2/3, 2. V is equal to, okay, 2/3, 2 and 2/3, 2/3 somewhere right here. I'm gonna cut this out in half here. Cut it out. So 2/3 is right here. See? Yeah. This one is your region S here. Okay. Well, in order to figure out the du dv here, where do they go from? You gotta extend this line here. I'm gonna extend this line here because this is the line right here. This line is, it's just a straight line here, so v equal to u, make it perfect. And then the other line is gonna be v is equal to 1/3 u. Okay. So that look good. We got the region S here. So in the region S, right, is it better to do du dv or dv du? Because we got to do the dA here. Dv du, very good, because you got to let v go inside, because we know v is between the two lines, so it's going to be dv du. So v is between the two lines, 1/3 u and 2u, and then u is between the two numbers. If you look at this, 0, u is equal to 3x plus 2y, v is equal x plus 4y. So I'm gonna multiply this by -3 here. U is equal to 3x plus 2y, and then -3v is -3x minus 12y. So that means we're gonna u minus 3v is negative 10y. So y is gonna be negative 1 over 10 u minus 3v. If you want to turn this into a positive, you can do so, because sometimes when you look at the solution, a lot of professors, they like positive, so you can turn it into a 110 3v minus u. If that would make you happy. Okay. To do the same thing here, I'm going to get rid of the y, so I'm going to multiply this one by negative 2. And this one is gonna be, yeah, gonna cancel out. How nice. Add them up. V minus 2u out the Jacobian. U V U V. Okay. X with U. It's gonna be so it's negative 2, so 205 with V negative 105. Oh man, I should have kept it the other way. Okay, so with Y is gonna be a negative 110 and 310. And 5 over 50 is 1 over 10. Okay, so that is the Jacobian is J. Yeah. Oh, we have the Jacobian. Now we're gonna sub it in and work it out. This is the 3x plus 2y over x plus 4y. S, oh, right here, the region S, 0 to 2, and u of 3 to 2u. In here, what do we have? In here, u over v. Oh, that's the Jacobian. 110 dv du. Aha, how nice. Work it out, and the integral here is pretty simple, so you guys can do this thing, right? Answer to be ln over 5. Example. Now let's have you to evaluate this thing here. Triple integral of xz dv, where E is bounded by a bunch of plane. Y equal x. Y equal x plus 2. Z equal x. Z equal to x plus 3. Z equals 0. Z equal 4. Huh? Yeah, don't bother to sketch this thing out. Y equal x. Y equal x plus 2. Z equal x. Z equal x plus 3. Z equal 0. Z equal 4. Trick here is that you can solve for this thing here. This would be y minus x equal to 0. Y minus x equal to z minus x equal to 0. Z minus x equal 3. Nothing you can do here. Z equals 0. Z equal 4. Based on here, right? You can let u to be y minus x. And then you know exactly where does the u go from. V to be z minus x. W to be z. Okay. How nice. The only shock part is you just got to solve for x, y, z in terms of uvw in order to figure out the Jacobian. Lucky for us, we have z is equal to w. Right? So I mean, you just have to solve for x and y. Right? It looks like we can do it backward here. Right? Now, uvw okay, so we know that z is equal to w. That take care of it. Well, from v equals z minus x, we know that x equal to z minus v. So x equal to w minus v. Okay, that's good. Okay, so another information here is that u is equal to y minus x. So y is equal to u plus x. Y is equal to u plus w minus v. I, j, k. Yeah. Partial x with respect to u, partial x with respect to v, partial x with respect to w, partial y with respect to u, partial y with respect to v, partial y with respect to w. Same thing here. Partial z. Okay. Get this thing out, and then we're gonna do a determinant of this thing. Okay. Well, x with u is gonna be look at x there. There's no u in here, so it's gonna be 0. How nice. With v is gonna be -1. With w is gonna be 1. Oh, how nice. It's very fast though. going to be a 1, -1, 1, and then for the z is going to be a 0, 0, 1. There are many ways to find the determinant of a 3x3 matrix. And one of the best way is the cofactor expansion. Okay, so meaning that you're gonna choose one column or one row to expand this out. The thing about why I write ijk is that you have a plus, minus, plus, so it go the same, right? Plus, minus, plus, yeah. So that's this. I can choose to expand this through the very first row. I'm gonna choose expand first row here. First row expansion. So you can get an idea of what is going on here. I'm not going to put the 3x3 on the exam. It's way too long. Right? So 0, right? And then you're going to cross this out and cross this out. See? And that will give you right? -1, -1, 0, 1, 1. Okay, next one is the -1 here. Right? Do the same thing. Cross this out. -1, 1. Zero, 1. And then for the last one is the +0. Cross this, -1, 1, -1, 1. As you can see from the cofactor expansion, right? We're just gonna have a -1 time -1 is 1. Fortunately, it is the positive number, so you don't have the absolute value this thing. But make sure if it's not, you got the absolute value though. It's the absolute value here, always. Well, this would be because I set it up this way, du, dv, dw, 0 to 4, 0 to 3, 0 to 2. X is w minus v. And then z is w. Oh, how nice, huh? The Jacobian 1 du, dv, dw. You can do this then here. It's pretty simple to do. Usually the answer run out of time.